All right, welcome back, everyone. Here we are at the third lecture in Chapter 2, and we will be continuing to build on what we learned in the previous lecture. Previously, we learned about atoms and elements. We learned about their structure, the different parts of an atom. So today, we're going to be taking that information and taking the next few steps. And as always, we start with our not really attendance questions. See if you can answer what is a valence electron and what happens when energy is converted from one form to another since it is inefficient. Go ahead and try to answer those questions. And hopefully you paused the video and tried to do that. So let's see. What is a valence electron? Well, a valence electron is an electron that's in the valence shell, which then brings the question, what is a valence shell? Remember, the valence shell is the outermost shell of an atom. Depending on how many shells the atom has, it could be the first shell, it could be the second shell, it could be the third shell, and on and on. It's just whatever the outermost shell is the valence shell, and the electrons that are found in that outermost shell are valence electrons. Those are going to be very important in today's lecture. Next, what happens when energy is converted from one form to another since it is inefficient? Well, remember, we can convert from one form of energy to another, but when we do that, some of it is lost as heat, and that's because it is inefficient. Some energy is always lost as heat when we convert from one form of energy to another form. All right, picking up where we left off last time, now we're going to start talking about joining atoms together, mixing atoms, mixing either atoms of the same element or atoms of different elements, and looking at all of the different things that could happen when we do that. And two terms that we're going to introduce now are molecules and compounds. And there's a little bit of overlap here. So they can be a little bit tricky if you don't pay close attention to the similarities and the differences. A molecule is any time we have two or more atoms chemically bound or chemically joined together. And it could be two atoms of the same element, like we see here with two oxygens joined together. O2, that's the oxygen that we breathe. It could be different elements joined together, such as carbon dioxide, CO2. That's the waste air that we breathe out. That is a carbon atom and two oxygen atoms joined together. It could also be water, H2O, two hydrogens and an oxygen joined together. So anytime you have two or more atoms, regardless of the element, joined together, that is a molecule. So let's look at compounds. Compounds are any time we have two or more atoms of different elements joined together, such as NH4, ammonia. NH4 is a nitrogen and four hydrogens joined together. So because we have nitrogen and hydrogen, different elements, that's a compound. It is not all the same element. So that is actually also a molecule. Water, H2O. Because it has two hydrogens and an oxygen, different elements, it is a compound, but again, it is also a molecule. Molecules are any element joined together. Compounds are always more than one element joined together. So, all compounds are also molecules, but all molecules are not necessarily compounds. Let that sink in. All compounds are also molecules, but all molecules are not necessarily compounds. If they are the same element, if it's all one element, it's a molecule but not a compound. If it is different elements, it is both a molecule and a compound. So now, moving on to mixtures. Most matter exists as a mixture, and a mixture, by definition, is just two or more components physically intermixed. And there can be different types of mixtures: solutions, colloids, suspensions. And solutions really are the one that we're going to talk about most in this class and in Bio 137. So we'll look at solutions here in just a moment, but first let's talk about the other two. Colloids, when we mix them together, we have the solute particles are larger than they would be in a solution. They scatter light, they don't settle out. But then, what is a solute? So let's talk about the parts of a mixture. We have solutes and solvent. So those are the two parts of a mixture. The solvent is the larger component. It is what does the dissolving. It is what the other parts are in. So usually this is water. It's not always water, but the majority of the time the solvent is water. And solutes are what are dissolved or suspended in the solvent. So let's just say we have a cup of salt water. Well, the water is the solvent and the salt is the solute. So in a colloid, the solute particles are larger than they would be in solution. And when we shine light through, the light is scattered. An example is Jell-O down here. Jell-O is a colloid. The solute particles, which is typically something like gelatin, sometimes collagen. But so in solution, the particles are pretty small. We'll talk about solutions in a moment. In colloid, the particles are a little bit bigger. When we shine light through, it scatters. So think about a cup of pure water or salt water or something like that. It's pretty clear. But if we look at something like Jell-O, when we shine light through, it kind of scatters that light. And if we let the Jell-O sit for a while, the solute particles are not going to settle out. They're going to remain in that mixture there. Another type that we'll talk about actually quite a bit in A&P is a suspension, because blood is a suspension. Blood is a suspension. And here, the solute particles, which are things like blood cells, proteins, things like that, they're very large. And if we let blood sit for long enough, or if we put it in a centrifuge, then those solute particles will settle out. if you've ever seen in a lab where they take some blood and they put it in a centrifuge, when it comes out, it's been separated into its components. The liquid portion, the solvent, is plasma, and the solutes are going to settle out after a while. But let's talk about solution. So solutions, we say, are homogeneous mixtures. Homo means the same. So homogeneous mixtures are the same throughout. Let's look here at this solution. This is something like salt water or sugar water or something like that. The particles, the solutes, are very tiny. They do not settle out and they do not scatter light. So this mineral water, this could also be salt water, this could be sugar water. It's an example of a solution. It's clear. We could let it sit there, we could put it in a centrifuge, we could do whatever, but the particles, the solutes, are not going to settle out. And where it is a homogeneous mixture, we can see it is the same throughout. And if we looked at this under a microscope, even a very strong microscope, it's going to look the same throughout. There are not going to be bits and pieces. Like if we looked at blood under a microscope, we would see clear spots where the plasma is. We would see red spots where the red blood cells are. We would see whitish purple spots where the white blood cells are. But in a solution, it's a homogeneous mixture. It's the same throughout. And we've discussed solvent and solute. Solvent is the larger portion. It's what does the dissolving. And again, like we said, it's usually water. Not always, but usually. And solutes are what are dissolved. They are the smaller pieces. And when we talk about solutions, we usually talk about it in concentration form. We will say something like it is a 20% sodium solution. And what that tells us is if we have a beaker with sodium water in it, 20% of that is sodium, the other 80% is water. We could also use milligrams per deciliter as the concentration. If you know anyone who has to test their blood sugar regularly, you may get a reading that's something like 95 on your glucose meter. And that is actually 95 milligrams of glucose per deciliter of whole blood. And lastly, we may see molarity, which is moles per liter. That's more of a chemistry concept. We won't really talk about it much in biology. But if you take a chemistry class, you use this all the time. Now, we will talk about solutions and concentration again in Chapter 3, and we will also talk about it in Bio 139. So make sure you understand what a solution is. Make sure you understand solvent and solute. And make sure you understand the concentration, especially the percent concentration. Now we've talked about mixtures and we've talked about compounds. So what's the difference here? In mixtures, there is no chemical bonding. There's no chemical bonding between the parts. In compounds, the components are chemically bound. In mixtures, we can filter something. We can separate the parts by physical means. Straining, filtering. But in compounds, we can only separate out the parts by breaking bonds. And in mixtures, they could be heterogeneous or homogeneous, like we talked about with our mineral water. That is homogeneous. It's the same throughout. In blood, we said it was heterogeneous. There's some parts where there's plasma, there's some parts where there's platelets, there's some parts where there's red blood cells. So it's different throughout. But in compounds are always homogeneous. Okay, so now we're going to talk about the periodic table and combining atoms again. Now, this periodic table is always going to be provided to you on exams where you need it. So you do not have to memorize this. But I did say you would get familiar with the periodic table because we will be talking about it quite a bit in this class. Now, we're going to, like I said, focus on those purple ones, especially the top 3 rows and a little bit at the start of the 4th. This is also available in your textbook in Appendix E. So if you want to have a printout or your digital textbook pulled up while you look at this, while we go through the rest of the lecture, it might be very handy because I will be referring to different parts of the periodic table. Remember the atomic number and the atomic mass and the atomic symbol. I will be referring to those over the next few slides. So now we're going to talk chemical bonding, the joining together of atoms. So why do atoms bond? What's the point? What causes it? What's the result? Well, atoms bond because they want their valence shell to be full. Think back to the last lecture. The first shell can hold up to 2 electrons. The second shell and everyone after that can hold up to 8 for purposes of our class. If there is not a full valence shell, then that atom will attempt to get a full valence shell by bonding. How does it do that? Well, there's a few different ways, and we're going to look at those over the next few slides. But it's going to come down mostly to something called electronegativity. Electronegativity is the strength with which an atom pulls electrons towards itself. The more an atom pulls an electron towards itself, we say the more electronegative it is. And if we look at our periodic table, the further to the right and the higher up on the table something is, the more electronegative it is, the more it will pull an electron towards itself. So for example, fluorine is really far to the right and really high up. It pulls electrons towards itself. But something like potassium, lower down and all the way on the left, it's not very electronegative at all. It doesn't have a lot of pulling force. And electronegativity is going to be a driving force in how an atom chemically bonds. So we're going to do a lot of drawing, and I really recommend having a lot of blank paper handy for this because some of the drawings will get a little bit big. We're going to have need of space. So let's pull up a whiteboard here. And we're going to do some drawing. First thing we're going to draw is going to be something called an ion. And then we're going to build on that with ionic bonds. All right. First thing we're going to draw is sodium. And if we look at our periodic table, sodium is all the way in the very first column, the third one down. It is atomic number 11, atomic symbol Na. So using our method that we learned before, there's our Na, so that's going to represent our nucleus. And if it has atomic number 11, that tells us it has 11 protons, but it also tells us it has 11 electrons. So let's draw our sodium. There's the first shell with 2. It has more than 2, so we have to add another shell. Remember, the second shell can have up to 8. There's 8, so now it's got a total of 10. But since it needs 11 electrons, it means we have to add a third shell. So that is sodium, atomic number 11. Let's go ahead and down here at the bottom, let's talk about how many protons it has. It has 11 protons. And let's talk about electrons. We're not concerned with neutrons. So we have 11 electrons, 11 pluses and 11 minuses. Like all other atoms in its natural state, sodium is electrically neutral. It has no charge. The number of positives and the number of negatives balance out. Let's practice a little bit more. Let's draw chlorine. Chlorine, if we look on our periodic table, it is atomic number 17. So you can pause the video and see if you can draw chlorine. I'm going to go ahead and draw it here on the right. Chlorine. If it's atomic number 17, it has 17 protons and 17 electrons. That means it's got 3 shells. And in the outermost shell, we've got 7 electrons. Let's go ahead and make our note down here. 17 protons, 17 electrons. So now we've drawn sodium, we've drawn chlorine. But let's take a look at some of the details that we've got here. Sodium has 1 valence electron. How many more does it need to have a full valence shell? It needs 7 more electrons. If it has 7 more electrons, it'll have a full valence shell and it'll be happy. Let's look at chlorine. Chlorine, how many more does it need in its valence shell? It needs 1 more. 1 more electron in its valence shell will make it full and it will be happy. Now, looking at the periodic table, we can see chlorine is all the way to the right. Sodium is all the way to the left. So which one is pulling more? Chlorine is further to the right, so it has greater electronegativity. It pulls electrons towards itself more. So chlorine is pulling electrons towards itself. It is pulling its own electrons towards itself. Sodium is pulling on electrons. It's pulling its own electrons towards itself. But chlorine and sodium, if they get close enough together, chlorine is also pulling on sodium's electrons. And sodium is also pulling on chlorine's electrons. But we said that chlorine has greater electronegativity. It pulls more. And it pulls so hard because of that much greater electronegativity, it will actually take one of sodium's electrons. I'm drawing it in red so it stands out, but all electrons are exactly the same. Once that sodium electron moves into chlorine, there is no way of knowing which of those electrons originally belonged to sodium. They are all exactly the same. So now what do we have here? Chlorine has a full valence shell. It's happy. It's great. Sodium, what happened over there? Well, it only had 1 valence electron. and that valence electron is gone. It is the valence electrons that create the shell. So if there is no valence electron there, the entire shell is non-existent. And what's the result? The result is now that sodium has a full valence shell, and it is happy. It's got a full valence shell. Chlorine has a full valence shell. Both are happy. But we end up with another situation. How many positives does sodium have right now? How many protons does it have? It has 11. How many electrons does it have? It only has 10 electrons. There are more positives now than negatives. It is no longer in its natural state. The positives and the negatives are out of balance. This is no longer sodium. This is sodium ion. It has a positive charge, and the way we denote that is Na with a little plus up in the top right. That means that it has lost an electron and now has a positive charge. Let's look at chlorine. Chlorine, what happens there? It's now got an extra electron. It still has 17 pluses, it still has 17 protons, but now it has 18 electrons. And we write that it's no longer chlorine, it's chlorine with a negative charge. That's called chloride. And we write that Cl with a little minus up at the top right. Na plus and Cl minus is what we end up with. Just a quick note before we see what happens here. Anytime we gain an electron, we write it with a negative sign. Anytime we lose an electron, we write it with a positive sign. So how do we know that that positive means we lost an electron? How do we know that it doesn't mean we gained a proton? Well, think back to the last lecture. Protons are always the same. There is no giving away or taking or losing protons. It is only electrons that we give away or receive. Okay, so both of these are ions. Sodium is a positive ion. Chlorine is a negative ion. So we have ions here. But we can be a little bit more specific. If it has a positive charge, it's actually called a cation. And if it has a negative charge, it's called an anion. Cations have lost an electron. Anions have gained an electron. Cations have a positive charge. Anions have a negative charge. And if that's hard to remember, one way that you can think about it is cations have a plus right there in the middle of the word. And anions are a negative ion. So that's one way that you can keep them straight. But what's the point of all this? What results from this? Well, if they were close enough, if sodium and chlorine were close enough that chlorine could take an electron, well, they're also close enough that the next step can happen. Sodium has a positive charge now. Chloride has a negative charge. What happens when you have the positive end of a magnet and the negative end of a magnet close together? They're going to stick. And we no longer have sodium and chloride. We have sodium chloride. They stick together like a magnet, and that is called an ionic bond. An ionic bond results when one atom takes an electron from another atom and the two ions stick together because of opposite charges. NaCl, by the way, is table salt. Every time you put salt on your food, this is what you're putting on your food. All right, so now let's move to something else. Let's talk about another type of bond, but first let's draw carbon. I'm going to go back to my black ink. While I do that, see if you can draw carbon. Carbon is in the second row. It is atomic number 6. And I'm going to draw while you do that. So there's what carbon should look like. Protons in the middle represented by the C. 2 protons in the first shell, 4 protons in the second shell, and now we're full. Or we've used up all of our electrons. We're not full. We still need 4 more electrons. We need to take 4 electrons, or we need to lose 4 electrons. But carbon is pretty much in the middle, so it's not very electronegative. It's going to pull on its own electrons hard enough that no one's going to take them, but it's not going to pull hard enough that it can take electrons from anybody else. Let's look at hydrogen. See if we can draw hydrogen. Hydrogen is actually the easiest one to draw because it's only got 1 electron. So it's got 1 shell with 1 electron in it. It is very weak when it comes to electronegativity. It's all the way on the left. So, who's going to take whose electron here? Neither. We're not going to take any electrons. Instead, we're going to share electrons. And what will happen is, if hydrogen and carbon get close enough together, they will pull on each other and they will bump together. And what we will end up with is something like this. Hydrogen and carbon are going to share electrons. Nobody is taking electrons. Nobody is losing electrons. They are sharing the electrons equally. Now, if we look, we can see in this area, let me change ink color. In this area right here, those electrons, one belonged to hydrogen and one belonged to carbon. But now they belong equally to hydrogen and carbon. The hydrogen there has 2 valence electrons now, which is all it needs because it's only got 1 shell. So hydrogen is full. Carbon, it's fuller, but it's not quite happy yet. But there's a lot of hydrogen around. And if other hydrogens are nearby, they will do the same thing. And the result is we now have 4 hydrogens that have full electron shells, full valence shells. Each of those hydrogens has 2 electrons now. And if we look at the carbon, carbon now has 8 valence electrons. It's happy. Its valence shell is full. Everyone here is happy. No one took electrons. No one gave away electrons. They're all sharing, and they're sharing equally. And we call that covalence, or a covalent bond. Co means together. Valent, referring to the valence shell. So everyone's valence shells came together. They're sharing electrons. And more importantly, they are sharing electrons equally. So keep that in mind. We will come back to that in just a moment. Right now, we will just call that a covalent bond. Let's draw another covalent bond. And let's begin by drawing oxygen. Oxygen is atomic number 8. I'm going to draw the O there to represent the nucleus. It's tough to draw oxygen sometimes because that O looks like it might be a valence shell, but it's not. So it is O for oxygen. And the first shell, there's our 2 electrons. It needs 6 more. So let's go ahead and draw 6 more electrons in the valence shell. There's oxygen with its 8 electrons, 6 valence electrons. And let's go ahead and draw a covalent bond with 2 hydrogen atoms, just like we did with carbon. Both of those hydrogens now have 2 valence electrons, which is all it needs in that first shell. Both of those hydrogens are happy. The oxygen now has 8 valence electrons. That's all it needs in that second shell. Oxygen is happy. This is another covalent bond. But this is different from hydrogen. Different from carbon and hydrogen. So when oxygen and hydrogen bond, it's a covalent bond. When carbon and hydrogen bond, it's a covalent bond, but they are not the same. If we look at oxygen on our periodic table, it's far to the right and it is high to the top. So oxygen is very electronegative. It is not electronegative enough to take the electrons from hydrogen. But it is electronegative enough that when it shares, it does not share equally. When we look at these shared electrons, instead of equal sharing like with carbon and hydrogen, here oxygen pulls more on those electrons. And as a result, those electrons spend more time closer to the oxygen side and less time closer to the hydrogen side. And what we end up with is an unequal sharing. And even though oxygen did not take electrons, he did not get a negative charge like we saw back with chloride earlier, he does become slightly negative. And the way we draw that is with this little guy right here, the Greek lowercase letter delta. But that just means slightly. The oxygen side of a water molecule is slightly negative. And the hydrogen side, since it doesn't hold on to the electrons as much, it is slightly positive. A water molecule has a covalent bond, but they do not share equally. They share unequally. So we call this a polar covalent bond. When we see the word polar, and we will see the word polar a lot in this class, it means 2 regions are different from each other. In this case, it's talking about one region, the hydrogen side of the water molecule, has a slightly positive charge. The other region, the oxygen side of a water molecule, has a slightly negative charge. Polar covalent bonding. Let's go back and look at our carbon hydrogen. This is non-polar covalent bonding. Everyone is sharing and they're sharing equally. By the way, we would write this CH4, 1 carbon, 4 hydrogens. This is methane gas. Going back to our polar covalent bond, we would write this H2O, 1 molecule of hydrogen, 2 molecules of hydrogen, 2 atoms of hydrogen, if I can spit that out. 2 atoms of hydrogen, 1 atom of oxygen. This, of course, is water. Water is a polar covalent molecule. Now, building on that, we are going to look at our last type of bond, and it's a little bit tricky. So we're going to keep this water molecule, but now we're going to zoom out. And when our book and when most places draw water molecules, they kind of look like little bitty Mickey Mouse. Our oxygen and our two hydrogens, and remember the hydrogen side is always slightly positive, the oxygen side is always slightly negative. Here's another water molecule, slightly negative side, like slightly positive side. Here's another water molecule. So these are the same thing, we're just zoomed out. Lots of water molecules. Now, when water molecules get close to each other, the positive regions and the negative regions are attracted to each other, again, kind of like magnets. So there is a little bit of a bond that forms between the positive side of one water molecule and the negative side of a nearby water molecule. And we can draw some more. Now, these bonds between nearby but different molecules that have polar covalent bonds, these bonds are called hydrogen bonds. So let's look at this. Let's clear up anything like common confusions. A hydrogen bond is not a bond between hydrogen and something else. Hydrogen plays a role in it most of the time, but hydrogen bond does not refer to simply a bond between hydrogen and something else. A hydrogen bond is a bond between a negative region of one molecule and a positive region of another molecule where we have polar covalent bonds. These bonds are very weak. These bonds are temporary. They don't last very long at all. They are constantly breaking and reforming, breaking and reforming. But there are lots of them. That's what allows water to stick to itself. That's what allows water to stick to other things. Hydrogen bonds are everywhere, and they are the result of nearby polar covalent bonds. And they act kind of similar to ionic bonds because it's an attraction between positive and negative. It's just in hydrogen bonds, it's a slightly positive and a slightly negative. No one's taking, no one's giving. It's just they're sticking together because of those charges. So that is our types of bonds. Let's go back to our PowerPoint and talk about chemical reactions. So chemical reactions are what happen when bonds are either rearranged or they are formed or they are broken. So those bonds that we just looked at, when they are formed, that's a chemical reaction. If we break them apart, that's a chemical reaction. If they go through a change, that's a chemical reaction. And we represent chemical reactions by using chemical equations, like we see down here at the bottom. They can be very, very small. They can be really large and complicated. But they always have some things and then an arrow pointing one way or the other way, or sometimes you may even see something that looks like either partial arrows pointing two directions or an arrow with a head on each side of it. But this is how we draw chemical reactions. And in a chemical equation, we have two parts. We have reactants. Reactants are what the arrow is pointing away from. It's what we're starting with. And products. Products are what the arrow is pointing towards. It's what we get out of the chemical reaction. And the relative proportion of each. So if we don't see a number in front of something, that just means there's one of them. It doesn't mean there is only a single hydrogen and a single hydrogen and a single H2 hydrogen gas. It just means the relative proportion. For every one hydrogen, we add one hydrogen and we get one hydrogen gas. But this could be trillions upon trillions of hydrogens. Or down here we see 4H and 1C gives us 1CH4. That just means for every 4 hydrogens, there is a carbon. That's what we mean by relative proportions of each. Now let's look at one other thing that's not mentioned on the slide, but we will often see some numbers down in the bottom left. Bottom right. The number down in the bottom right just tells us that there are that many of that atom chemically joined together. So here we have 2 hydrogens chemically joined together. Here we have 4 hydrogens chemically joined together with a carbon. That's what we drew with our nonpolar covalent bond. Number to the left, how many of it there are. Number to the bottom right, how many are joined together chemically. So what types of reactions are there? There's several. One of them is a synthesis reaction. This is anabolic. Anabolic is taking things and joining them together. We are forming bonds. We take something, several small things, and make one big thing. A decomposition reaction, which is sometimes called a catabolic reaction, is exactly the opposite. It breaks bonds. We start with something big, and we end up with something small. And we have exchange reactions. These are synthesis reactions and decomposition reactions happening at the same time. I refer to this sometimes as, think about your grocery shopping. You go into the grocery store and you have money. So you and your money are bound. You go into the grocery store has groceries. The grocery store and the groceries are bound. You get to the checkout, you go through this reaction. You and your money, the bond there is broken as you give the money away. You pick up the groceries and leave with them. The bond between the grocery store and the groceries was broken. Now there's a new bond between the grocery store and your former money, and another new bond between you and the groceries. So we just exchanged. One way that you will sometimes see this written is AB plus CD goes through a reaction, and we end up with AC and BD. So the bond between A and B was broken. The bond between C and D was broken. We shuffled some things around. We end with a bond between A and C and a bond between B and D. And we have redox reaction. This is oxidation, reduction. Oxidation, reduction reactions. That's where the redox comes from. Redox reactions are a type of exchange reaction. Here, we're going to have electrons that are moving from one spot to another. And what we end up with is, I'm going to draw, actually I'm going to use the whiteboard for this. Let's use the whiteboard to draw a redox reaction. Now, I will warn you in advance, this is going to look pretty messy, but we'll make it make sense. A common redox reaction is cellular respiration. We have C6H12O6, which is glucose, plus 6 oxygen molecules. They go through a reaction, and the reactants are 6 molecules of CO2, 6 molecules of water, and energy. This is how your body takes the food that we eat and turns it into energy that our body can use. This is a redox reaction. So let's look to see what that means. In a redox reaction, we have electrons that are moving from one place to another. We have some molecules that are going to lose electrons. And we have some things that are going to gain electrons. And if we lose electrons, we say that molecule is oxidized. If we gain electrons, then we say that molecule is reduced. We'll come back to that in just a moment. This is just to introduce the terms. Losing electrons is oxidation, gaining electrons is reduction. So, this is a redox reaction. The C6H12O6 plus 6O2 leads to 6 CO2 and 6 water. But if we're talking about gaining and losing electrons, where are the electrons? They're hidden. And that doesn't really help us very much in biology. But luckily, in biology, we have a little bit of a cheat. We can take the word electron and replace it with the word hydrogen. This does not work in chemistry, but in biology, it works for us. So, now if we say losing hydrogens is oxidation, gaining hydrogens is reduction, we can look at that. And what we can do is first look at the reactants. Remember, the reactants are what the arrow is pointing away from. Where do we see a hydrogen? Right there in the glucose. And if we look to see, if we remove H from that, we are left with CO. Now let's look on the right side at the products. Do we see anywhere where there is a C and an O without an H? Don't pay attention to the numbers. Just look for a C and an O without an H. Right there. So, glucose lost hydrogens to become CO2. We say that glucose was oxidized to carbon dioxide. Now, what about the reduction part? Gaining hydrogen. Is there anywhere on the left where we have something that does not have a hydrogen, but if we look over on the right, it does have a hydrogen? Well, oxygen over here does not have a hydrogen with it, but oxygen over here does. So during this reaction, we gained hydrogen. We say oxygen was reduced to water. There's our oxidation reduction reaction. Losing electrons, or in this case hydrogen, is oxidation. Gaining electrons, hydrogen, is reduction. One of the most common questions, and I would say probably many of you have this question right now, is if we are gaining something, why is it called reduction? Well, think about what it is we're really gaining. We are gaining electrons. And what do we know about electrons? They have a negative charge. So by gaining negative charge, the overall charge goes down. It's reduced. So that is our example of a redox reaction. What's the point of these images that I have? Well, losing electrons is oxidation. Gaining electrons is reduction. And Leo the lion is saying, grr. So that's one way to remember who's losing electrons, who's gaining electrons. Another way to remember it is oxidation is losing electrons. Reduction is gaining electrons. And there's our oil rig. Oxidation is losing, reduction is gaining. Whichever one of those sticks for you, those are some ways to remember what's what. Now, when we go through chemical reactions, energy is going to be moved around also. We're going to either gain energy or lose energy. So we have energy flow and reactions. Some reactions give off energy. Some reactions require energy to be put in before they will happen. An endergonic reaction requires energy to be put in, and an exergonic reaction releases energy. Energy is exiting during an exergonic reaction. Energy is entering during an endergonic reaction. Now, what about rates of reaction? How quickly do reactions occur, and how can we change those rates? Well, temperature. Increased temperature will increase the rate of a reaction. Concentration of reactants. If we have more reactants, then the reaction can happen faster. It's because we've got more to work with. Particle size. The smaller the particles, the faster the rate of the reaction, because those particles can move around quicker. And the use of catalysts or enzymes. These are just molecules that speed up reactions. So if we have a catalyst, if we have an enzyme present, that will allow the reaction to happen faster. All right, I know that was a big lecture there. That was probably our biggest one so far, and it will be the biggest for a while. So it's recommended watch that again a time or two, let that all sink in, ask questions as you have them, and then I will talk to you in our next lecture where we will talk about non-organic biochemistry. After that, we will have one more lecture, organic biochemistry. All right, please reach out with those questions, and I will see you in our next lecture.